last idea we're going to look at for the moment with complex numbers is this particular problem of roots of unity. We saw that Demoivre's theorem is quite useful for finding roots. So we're restricting it basically to unity, things that have a modulus of 1. So it could be negative 1, it could be positive 1. So those solutions to those equations, hence the title I guess, are known as the nth roots of unity. Now when you plot these points on the Argand diagram, it's like I was saying to you the other day, whenever you're finding roots, solutions are evenly spaced around the Argand diagram. So because these ones are of unity, they'll all lie on the unit circle. So you'll end up with a regular n-sided polygon sitting on the unit circle. So let's have a look at z to the power of 5 is equal to 1. So using Demoivre's, we can straight away say, well, because it's unity, I don't have to worry about the modulus, because the fifth power of 1 is going to be 1, the fourth power of 1 would be 1, the cube root of 1. So it's always going to be 1. So it's the argument we're interested in. Now the argument of 1 is 0, but then we add the 2 pi k to allow going around the circle as many times as we like. And then we divide it by whatever the power is, in this case 5. So I need 5 solutions, and I want 5 consecutive solutions. But you'll notice instead of going 0, 1, 2, 3, 4, I've gone 0, plus or minus 1, plus or minus 2, which of course are still 5 consecutive solutions. But the advantage of doing that is it brings out the conjugate solutions. Because the coefficients are real in this particular question, we know that any imaginary solutions will appear in conjugate pairs. So by going plus or minus, it brings them out straight away rather than having to search for them. So sub in 0, we get cis 0. Well, that's the obvious answer, I guess, because cis 0 is 1. Yes, 1 would be a solution to z to the power of 5 is equal to 1. But cis 2 pi on 5 and its conjugate cis minus 2 pi on 5, cis 4 pi on 5 and its conjugate cis minus 4 pi on 5. So there's our 5 solutions. So if I was to draw them, there's the first solution, the easy one that we know that is 1. Remember, they're evenly spaced. So my next solution, I can go, well, I know I'm going to go around 2 pi and 5. But its conjugate must be there as well. So cis minus 2 pi and 5. Then I'll go around another 2 pi and 5. There we are at cis 4 pi and 5. But its conjugate must be there as well. And sure enough, we end up with a pentagon, which lies on the unit circle. So again, it's a case of, once you've got the first one, you can create all the other ones quite easily with the picture, because you know how far you're going to rotate each time, and you know the conjugates have to be there in this particular problem as well. So all right, we'll stick with that one. We've got our 5 roots of unity. So we're going to show that if omega is one of those solutions. Now, the thing with it is, I can't just say, oh, I'll assume omega is this one. What I'm saying is, omega could be any of them, and this will work. So omega, when they say the complex root, they mean, well, it's any of the solutions, but not the real one. So not 1. It could be any of the other ones. But then omega squared, cubed, power of 4 and power of 5 will also be solutions. Well, I can do this by playing with index laws. So z to the power of 5 is equal to 1. Now, we've just been told omega is a solution. Therefore, omega to the power of 5 equals 1. Well, if omega to the power of 5 equals 1, then omega to the power of 5 to the power of 5 would be 1 to the power of 5, which is 1. So omega to the power of 5 must also be a solution. Okay, but hang on a sec. Omega squared to the power of 5, I want to work out if this is a solution. I could rewrite that as omega to the power of 5 squared. And we know omega to the power of 5 is 1. 1 squared is 1, so oh yes, omega squared works when we sub it in. So omega squared is a solution. Well, let's see if omega cubed is. Sub that in, I get omega cubed to the power of 5, but I can play around with the indices. That's the same as omega to the power of 5 cubed. We know omega to the power of 5 is 1. 1 cubed is 1. So yes, omega cubed is a solution. And well, let's sub in omega to the power of 4. Omega to the power of 4 to the power of 5 is the same as omega to the power of 5 to the power of 4. Omega to the power of 5, that's 1. And 1 to the power of 4, that's 1. So yes, omega to the power of 4 is a solution. Now, unless they actually ask me to do that, it is okay to assume that, well, if omega is a solution, then omega squared. We don't want to have to go through that hassle every single time. It is fair enough. But if they do happen to ask us to show that it works, then that's what we do. We just play around with index laws and we can easily show they're all solutions. Okay. Well, now they want us to prove that 1 plus omega squared plus omega cubed plus omega to the 4 is equal to 0. There's several ways we can actually do this. The first way I can say is, well, hang on, we just said these were the 5 roots of the equation. So the sum of the roots must be minus b on a. Now, I've done 2 things here. Omega to the power of 5, well, I know that's equal to 1, so I've substituted 1 in. Minus b on a, well, if you have a look at our equation, there is no term for b, so the coefficient is 0. And so there it is. But via the sum of the roots, they must add up to give 0. So that's one way we could do it. Another way we could do it is we could look at this equation and say, well, let's factorise it. Omega to the power of 5 minus 1 would factorise to be omega minus 1, and then in the other one we get 1 plus omega squared plus omega cubed plus omega to the power of 4. Remember, if you want to factorise anything to the power of n minus 1, omega minus 1 would be the first factor, and then basically just all the powers would be in the other one, going down to the power of 0, which is, of course, 1. Well, it must be the case that 1 plus omega squared plus omega cubed plus omega power of 4 equals 0, because omega minus 1 can't equal 0. Because remember, we said omega was the complex solution. It wasn't equal to 1. So therefore, the only other possibility is that the second factor is equal to 0. Right? Because we know omega does not equal 1. So the first factor can't equal 0, therefore the second factor must equal 0. So that's one way we could do it. But there's another way. Have a look at that. Well, that's just a geometric series. So we could use our sum of a geometric series with first term's 1, the ratio is omega, I've got 5 terms. So if I sub into our formula, we get 1 times omega to the power of 5 minus 1 over omega minus 1. But oh, hang on a sec. We know omega to the power of 5 is equal to 1. So that's equal to 0. So there's a third way you could do that. So up to you, I guess, whichever way you want to approach it. I think sum of the roots is probably the quickest, because you just go da-da-da-da, oh, sum of the roots, done. But that's just a personal preference, I guess. All right, now we're going to create a new quadratic equation. The roots are omega plus omega to the power of 4, and the other root omega squared plus omega cubed. Now, well, sum of the roots then would be omega plus omega to the power of 4 plus omega squared plus omega cubed. If only we knew what that was equal to. Hang on, we do. Go back to what we proved right back there in part 2. We just proved 1 plus omega squared plus omega cubed plus omega 4 is equal to 0. Therefore, omega plus omega 4 plus omega squared plus omega cubed must be negative 1. So we know the sum of the roots. Okay. Well, what about the product of the roots? Expand out. Ugh. Oh, but hang on a sec. Omega to the power of 5 is equal to 1. So that omega to the power of 6 is the same as omega. And that omega to the power of 7 is the same as omega squared. And look at what we got again. Omega squared, omega, well, again, that's equal to negative 1. So we can create our quadratics. We know all quadratics can be written as, well, let's say x is the pronumeral, x squared minus the sum of the roots, x, plus the product of the roots. So our equation would be x squared plus x minus 1 equals 0. This time we're told omega is one of the complex, so again it can't be the obvious real solution, cube root of unity this time. Use that fact, use the fact that 1 plus omega squared is equal to 0. So in other words, they're saying, don't worry about proving it. It's another one of those things that they don't ask us to prove it, it's okay to quote it. And they're even telling us you can quote it. We're going to work out 1 plus omega squared to the power of 3. Well, it's a lot easier to cube a single term than it is to cube two terms. Again, we know 1 plus omega squared is equal to 0. So if I rearrange that, I get the 1 plus omega squared is minus omega. Cube that, I get minus omega cubed, but we're talking about the cube roots of unity, so omega cubed is equal to 1. So therefore, ours is negative 1. So basically, whenever you're manipulating, there are just two facts that you know. The omega to the power of n, whatever the power is equal to 1, or 1 plus omega squared up to n minus 1 is equal to 0. And you just play around with those two ideas. So now, if we got this fraction, I could create an algebraic fraction denominator, but look at the denominators. There's two terms there. A lot easier to turn them into one term. And I get 1 plus omega, that's the same as minus omega squared. 1 plus omega squared, that's the same as minus omega. Those two fractions are easier to add than the line above. Common denominator would be omega squared. I get minus 1 minus omega. But hang on, minus 1 minus omega, that's omega squared. So I have omega squared and omega squared. Oh, the answer is just 1. Now, it's no surprise a lot of these answers turn out to be 1 and minus 1 because we're playing with roots of unity. So but don't just assume it's going to be 1 or minus 1. We're going to create a cubic. The three roots are going to be 1, 1 plus omega squared. Okay. Well, I know one of the factors straight away because 1's a real number, so I know z minus 1 is a factor. In the other one, I must get a quadratic, and in that quadratic, again, z squared minus sum of the roots, so that'll be 2 plus omega squared, plus the product of the roots, so when we multiply those two together, we get 1 plus omega squared plus omega cubed. Okay, let's tidy those up. Oh, there we go, bang, straight away. Because, remember, 1 plus omega squared, that was equal to 0. So therefore, I'm just left with 1 there, so I've got minus 1z. In the other one, well, 1 plus omega squared, that's 0. So I've only got omega cubed. Oh, that's 1. So I get plus 1 in that. There it is. I suppose we could expand it out to see what it actually looks like. But I mean, that is a cubic equation. It answers the question. But if we look at what it actually is, expand it out, tidy it up. Oh, look at that. It's lovely and symmetric. You've got the 1 minus 2, 2 minus 1. Looks quite nice. We're going to solve this equation. Whoa, a pentic. But again, you'll notice the pattern of this is like the sum of the roots. So an easier question to solve would actually be if I had that right-hand side equals to 0. Because I know that would be z to the power of 6 minus 1. It's all right. And I know the solutions of z to the power of 6 minus 1. Cis 2 pi k on 6. And I need 6 consecutive solutions. So I'll start at naught, then I'll go plus or minus 1, plus or minus 2. Still another one I need, so I could use minus 3 or plus 3. Well, I'll use plus 3. Prefer positives. Okay, so remember this is the equation I want to solve, and I'm saying, too difficult, I'll solve this one instead. So I'll multiply top and bottom by z minus 1, thus on top creating the one that I know the solutions for. So it'll have exactly the same solutions. I just won't include the solution z equals 1 because that would create 0 on the bottom of the fraction. So the solution to this pentic must be the 5 other solutions. So there they are. Cis pi and 3, its conjugate. Cis 2 pi and 3, its conjugate. And cis pi is the other one we end up with, which is negative 1, of course. So this one I could actually put into a plus ib form because they're all exact values. I could work those ones out quite easily. So a half plus or minus root 3 on 2i, minus a half plus or minus root 3 2i, and then just negative 1 as well. And once again, you'll notice the symmetry of that, we're just missing that one that would complete the six-sided figure, which is of course a hexagon, but we're just missing that one solution. Here's a very old question now. It comes from an HSC paper. Here they were talking about the 9th roots of unity. And this time they said it's going to be this specific solution. So rather than saying it could be any of the solutions, they were saying omega will be this specific one. And they want to then show that, all right, omega to the power of k will always be a solution. K. What z to the power of 9 equals 1 is basically what we want to solve. If I was going to solve that, 2 pi k, remember cis of 1 is 0, so no need to write the plus 0 down, divided by 9. This time, because of the nature of the question, rather than going conjugates, I actually listed it as 0, 1, 2, 3, 4, 5, 6, 7, and 8. Well, de Moivre's theorem says cis of 2 pi k on 9, I'm using it in reverse now, it could have been cis 2 pi on 9 to the power of k, because de Moivre's would have put the k back in. But hang on, cis 2 pi on 9, that's what they told me omega was. So in fact we now have omega to the power of k, where k is 0, 1, 2, 3, 4, 5, 6, 7, 8. I just chose consecutive ones, but any integer is going to work. Okay. So there it is. They followed it up with the standard question, but slightly rewritten, just to try and trick people. You go, oh damn, if only it was 1 plus omega squared and all that, I'd be able to do this. How am I going to do it? But of course it is the same one. All right, well, there's my equation. Which way did I go? I said, oh, well, therefore 1 plus all of those is equal to 0. Sum of the roots. I guess the quickest way. Oh, hang on. How about I move that 1 to the other side? Bingo. There we got it. So really, part 2 was the standard question, but rewritten to just try and trick those that just, I don't know, rote learn or whatever they did, rather than thinking about the question. Hence show that when we multiply these 3 cosine functions together, well, not functions, sorry, those cosine terms, we get 1/8. All right, how have I done it? I've factorised z to the power of 9 minus 1. Now, of course, it would be z minus all the solutions, okay? Which I can rewrite like so. Whoa, how'd I get that? Because notice when I wrote it, interestingly with the powers, I didn't go 1, 2, 3, 4, 5, 6, 7, 8. I've gone 0, 1, 8, 2, 7, 3, 6, 4, 5. Conjugates. The conjugates will always add up, the powers will always add up to be the n. So in this case, they'll always add up to be 9. So I know that the 8 and the 2 will go together as conjugates. I know that the 8 and the 2, the 8 and the 1 would go together as conjugates. The 7 and the 2, the 3 and the 6. And if they're conjugates, then I know I can create a nice quadratic where the middle term is minus twice the sum. But if I'm talking about conjugates, twice the sum, well, the sum, the imaginary part's going to cancel because you're going to have plus I minus I. So I'll get twice the real part. Well, remember it's cis 2 pi on 9 and so on and so on. So the real part is, and this is where you've got to be careful if you're using cis notation, don't write cis down because now it's cos, not cis. I'm dealing with the real part. So it'll be twice cos 2 pi on 9. The product, well, a number times its conjugate, z times z conjugate, is the modulus squared. But remember, we're dealing with roots of unity, so the modulus is always 1, so the product is always 1. So now, go to the next one. Well, that'll be the same, but now it's cos 4 pi on 9, and the product's 1. Then 6 pi on 9, and the product's 1. 8 pi on 9, the product's 1. So I've got all these things multiplied together. I just need a clever substitution for z here to make the z squared and the 1 go away. How could I make the z squared and the 1 not be there? That's it. if you let z equal I, because the z squared will become -1, that'll get rid of the +1, and I'm going to get the product now, cos times cos times cos. So, before I did that, you'll notice cos 6 pi 9 is an exact value. So I changed it there. That's why you'll notice in what they're trying to prove here, there's only 3 coses, whereas we've got 4 parentheses with cos in it. That's because one of them we can work out. Let's sub in z equals I into everything. So on the left-hand side, we'll get I to the power of 9 minus 1. Then we'll get I minus 1. Minus 2 cos 2 pi on 9i minus 2 cos 4 pi on 9i minus 2 cos 8 pi on 9i. I can factorise out all those negatives. I can factorise out all those i's. I9 minus 1. Well, hang on. I to the power of 4, you're back to 1 again. So I to the power of 8, I must be back to 1 again. So I to the power of 9 is just I. So the left-hand side I've got I minus 1, which will end up cancelling very nicely with this I minus 1. Then all those i's. I. It's I to the power of 4, of course, that I've factorised out. Those negatives I've factorised out, so we can tidy that up a bit. The 2's I can bring out as well. 2 times 2 times 2 is 8. We're almost there. So 8, divide by 8. Bingo. We have our answer. Hang on. Yeah, no, that's what we wanted, wasn't it? Pi 9, 2 pi 9, 4 pi 9. Let me just go back. Oops. 2 pi 9. Hang on. What happened? I had 8 pi on 9. There's the step right there. We didn't want 8 pi on 9, we want a pi on 9. But 8 pi on 9 is an obtuse angle, so I'm saying it's in the second quadrant, negative. The acute angle would be pi on 9. So that's how I ended up getting my answer there. Alright, fun roots of unity questions. So several there to play with. As I say, that brings us to the end of our first look at complex numbers. They won't be going away.